In this section, we're going to look at the moment of inertia of solid objects. Moment of inertia of solid objects. So far, we've looked at about how to calculate moment of inertia of a system of particles. Now we want to look at moment of inertia of solids. Okay, so that's of course continuous distribution of particles. So let's say this is the solid object, and let's say this is the axis of rotation. So what we can do is we can take a representative element over here. We call that, let's say, dm. Okay, and then we take the perpendicular distance of this one. Okay, so let's call the moment of inertia of this mass dm di. Okay, so we have di equals the mass of the small mass element dm times the perpendicular distance from the axis squared. This is just a representative element. Okay, then you do that for all the mass elements and you add them together. That's an integral. Okay, so you've got the integral of di, this adding up all the moment of inertia of all the particles over here. We have the integral r perpendicular squared dm. Okay, so that is the moment of inertia of continuous distribution of particles of solid. This is simply the integral of r perpendicular squared dm. Okay, you take a small mass element, you obtain the moment of inertia of that small mass element, and then integrate over the whole mass. Okay, over the whole mass of the object, over the mass elements of the solid. So that's how you calculate moment of inertia for a solid object. You take a mass element, you obtain an expression for that moment of inertia, and then just add them up together, which means integration in calculus. Okay, so we're just going to demonstrate the use of this formula using some examples. So let's start with the first example. So let's say obtain the expression for the moment of inertia of a uniform rod of mass m and length L about an axis that passes through its midpoint perpendicularly. Okay, so here's the problem. We have this rod over here, its length is L. We want to calculate moment of inertia about an axis that passes through its midpoint. Okay, so let's use this axis. Let's say it's our y-axis, and this is the x-axis. Okay, and the length is L, so that means this goes from negative L over 2 to L over 2 over here. This is the value of x. So we have to take a representative element, this one over here. So let's say this is our representative element. Let's say the mass contained in this mass element is dm. Of course, let's be x, and then of course this will be dx. Okay, this the length of dm. All right, and so we're going to an expression for this for the moment measure of this one, and then we'll integrate. Okay, so the perpendicular distance between this axis and this mass element is x, right? So the moment inertia of this mass element over here is we can say di equals the integral of the distance is x, so you've got x squared dm. Okay, and now we want to change this integral to an x integration over here, right? So we have to replace this somehow in terms of x. So what we can do is we can use the concept of density. The rod is uniform, so that means the density is uniform. Okay, so let the density which is constant because it's uniform be lambda. Okay, so the lambda would be the mass dm divided by dx. Okay, but since also it's uniform, this also equals total mass divided by L. This is linear density, mass divided by length. Okay, well, you can obtain this very easily. Let's say you've got dm by dx. Lambda is a constant, so you've got dm equals lambda dx. You integrate, you get mass over here. You integrate, you get lambda times L over here. So that's how you get lambda equals m over L. Okay, but it's uniform, so you just divide the total mass by the length. Now from this relationship, you see this relationship over here, dm dx equals total mass divided by L, implies dm equals m over L times dx. So that means we can replace this dm over here by this one, and then we can integrate over x. Okay, so this is the integral, of course. So you've got the moment of inertia is the integral of x squared, and this is dm. We've got m over L times dx, and the value of x, you see, this is a representative element, but could be anywhere. So the value of this x ranges from negative L over 2 to L over 2. So the integral goes from negative L over 2 to L over 2. Okay, that's what we have to calculate. So we'll take the constant out, which is m over L, and then of course the integral of x squared is x cubed over 3, and that goes from x equals negative L over 2 to L over 2. That's it. So this equals m over L. Okay, so at L over 2, this would be L over 2 cubed divided by 3 minus negative L over 2 cubed over 3. Okay, so this is m over 3L. Okay, this is L cubed over 8, and this minus the negative of L cubed over 8. Okay, so what's that? We've got m over 3L, and then this is twice of this, so it's going to be L cubed over 4. Okay, so this L cancels with this L over here, so you get m L squared over 12. Okay, so that's moment of inertia. So this is the moment of inertia about an axis that passes through the middle of the rod, or the center of mass, perpendicularly. Okay, now let's do another example. So let's try to show that the moment of inertia actually depends on the axis of rotation. Now let's put the axis of rotation at the left end. Okay, repeat the previous problem. Let's say preceding problem about an axis that passes through through the left end perpendicularly. Left end perpendicularly. Okay, now we have the same rod. We're just going to change the axis. Okay, this is the axis. We've got the uniform rod. Now this is our axis of rotation. Okay, so we're trying to obtain moment of inertia of this rod about this axis of rotation. So let's be our x-axis. Okay, so this is starts from x equals 0 and goes to x equals L. So length is L. Okay, so now we're going to take a representative mass element over here. So let's say mass M is contained over here, and let's say the size of this mass element is dx, and of course this is x over here. Okay, so the moment of inertia of this mass element over here, we call di, is this perpendicular distance squared times dm. Okay, but the density is uniform. So the density is a constant, that is dm divided by dx, the density, but this uniform also equals m over L. So that tells you dm equals m over L times dx. So we integrate this equation, we get the integral of x squared dm, and then we substitute this one, we get m over L, the integral of x squared dx. Now the value of x changes from 0 to L. Okay, so this goes from 0 to L. So what we have is m over L, and this is x cubed over 3 going from 0 to L. So this is m over L, and this is L cubed divided by 3. So 1L goes with 1L, so it becomes 2. This becomes 2. So that is m L squared divided by 3. So you see the moment of inertia about an axis passing through its midpoint was m L squared over 12. But when the axis changes, the moment of inertia also changes. So moment of inertia depends on the axis of rotation. Okay, so we have moment of inertia equals ml squared over 3. All right. Another example. Let's say obtain an expression for the moment of inertia of a uniform ring of mass m, and let's say and radius r, about an axis that passes through its center perpendicularly, through its center perpendicularly. Okay, so that's what we have. We have this ring over here, and the x rotation is perpendicular to the plane of the paper. Okay, so basically the perpendicular distance between any mass element over here, let's take the mass element over here, let's call this dm. Okay, its perpendicular distance is the radius, and that is constant for any mass element over here. Okay, so the moment of inertia of this mass element is di equals, you see, this is the perpendicular distance r squared, and then times the mass dm. All right, now we integrate this, so you get I equals the integral of r squared dm. But you see the radius is a constant, so this is just r squared the integral of dm, but this is adding all the mass elements dm, so basically this is the mass of the ring. Okay, so the moment of inertia of a ring is simply m r squared. Okay, so the moment of inertia of a ring of mass m and radius r is simply mass times its radius squared. Okay, now instead of a ring, we're going to deal with disk. Example, let's say obtain an expression for the moment of inertia of a uniform disk of mass m and radius r. Okay, now we have a ring, I mean not a disk. So this is let's say this is our disk. Okay, and this is, I should say, about an axis that passes through center perpendicularly. Radius r, let's say about an axis that passes through its center perpendicularly. Okay, so our axis is like this, perpendicular to the plane of the paper. Now this is a full disk, it's not a ring. Okay, it's a full disk. So what we can do is, we know how to do the moment of inertia of a ring, right? So we can take our mass element to be a ring. Let's say this ring over here is our representative ring. Okay, our representative link. So let's say its radius is r, okay, and let's say its thickness is dr. So the thickness of this one is dr, its radius is r, and then of course the radius of the disk is capital R. Okay, so this is our representative mass element. So its mass is going to be dm. Okay, so we have di, this is a ring. The moment of inertia is the mass times the radius squared, so it's going to be the radius squared times dm. Okay, and to find the total moment of inertia, we're just going to add up all the rings and the radius changes, right? So the total moment of inertia would be the integral of r squared dm as the value of the radius changes from 0, this a point over here, to a radius r. That's what we have to do. Okay, but this is r, so we have to express this mass element in terms of r to be able to do this integral. Okay, so what we can do is, we can use the concept of density. The areal density is usually denoted by sigma, so that's a constant, right? So we can say this is areal density, so the density is mass divided by area. Okay, so what's the area of this ring? Its thickness is dr. The thickness of this ring is dr, and its radius is r. So the area is 2 pi r circumference times its thickness dr. Okay, so we have a thickness dr over here. All right, so the area of this mass element is 2 pi r times its thickness dr. Okay, but the density is a constant, so we can also express it as total mass divided by total area of the disk, which is pi r squared, because the density is a constant. So we have the following expression for dm. dm equals mass over pi r squared times 2 pi r dr. Okay, so let's replace that over here. So you've got moment of inertia. Let's take the constant. You've got m, pi goes away, so you've got 2 over r squared, and then the integral of r dr, where r is changing from 0 to the radius of the disk r. Okay, so this one is 2m over r squared, and this integral is r squared over 2 going from 0 to r. Okay, so you've got 2m, and this is over r squared. Okay, and then you've got r squared over 2. Oh, this is a square, I'm sorry. This is a square. So it's going to be r cubed. Well, there's an r over here. There's r over here. So this is the square. There's r over here. So the integral is 4. Okay? I forgot this r over here. All right. So you've got r4 over 4. Okay? So that gives you m r squared over 2. So the moment of inertia of a disk is the mass times the radius squared divided by 2. Okay? So you see, we have r squared, dm is given by this expression. This pi cancel this pi over here. So we get 2m r dr over r squared. Okay, and so you get r squared over here, we get r cubed, and the integral of r cubed is r4 over 4. All right, so that is the moment of inertia of a disk. Now let's look at the moment of inertia of a cylinder. Obtain an expression for the moment of inertia of a cylinder, let's say of mass m, radius r, and length L, about an axis, let's say about its axis. Okay, so we have the following over here. This is the cylinder. Over here. Okay, so the radius is r, the length is L, and total mass is m. So now we know how to obtain the moment of inertia of a disk. So we can take our mass element to be a disk. Okay, a disk. Let's say its length is, now I'm going to use my z-axis over here. This is going to be, let's say the axis goes through this axis. So this is the axis for rotation over here. Okay, and the length is, let's say this is the origin over here. So this length is L, so this will go from 0 to L over here. All right, so we take this disk R as our mass element over here. Okay, this is a disk right over here. So the disk has a radius R, but let's say its size is dz. okay? This thickness is dz. So this is z, this is z-axis, okay? So you've got this representative element, this is z, and this is dz, okay? So we know that the moment of inertia of a disk is its mass, let's call dm, this is a representative element. Now its radius is r, the radius is not changing, so this will be r squared over 2, all right? So that is the moment of inertia of this disk over here of side dz and radius r, okay? So we have, we're going to integrate now. So the integral of di equals the integral of dm r squared over 2. But this is a constant. All the disks over here have constant radius over here. So this is r squared over 2, the integral of dm. But the integral of dm is the total mass. So you see, the moment of inertia of a cylinder about an axis that goes through its axis is simply mass r squared divided by 2, just like the formula for a disk. All right. Now we're going to look at an important theorem called the parallel axis theorem. Parallel axis theorem. Okay. Now, the moment of inertia of a solid depends on the axis of rotation. Okay. So this theorem helps you to relate the moment of inertia about an arbitrary axis to the moment of inertia about an axis that is parallel to the axis and passes through the center of mass. Let's say you have this object over here. Let's say the center of mass of the object. Okay. So let's say we know the moment of inertia about this axis. So let's call this moment of inertia about an axis that passes through the center of mass. Now suppose you want to obtain the moment of inertia about another axis that is parallel to this axis and separated by a perpendicular distance d. Okay, let's call that moment of inertia I. This theory says that if the mass of the object is m, the moment of inertia about this axis equals the moment of inertia about the center, about the axis that passes through the center of mass, plus mass times the perpendicular distance between the two axes squared. Okay. So this one usually for regular objects, such as cylinder, for symmetric objects such as cylinder, sphere, and so on, you can find an expression for this one in tables in textbooks, and then you can obtain moment of inertia about any axis that's parallel to that axis using this theorem that we call the parallel axis theorem. Okay. So in this formula, ICM, this is moment of inertia about an axis that passes through the center of mass, Okay. Now this moment of inertia I, this is moment of inertia about an axis that is parallel, that's important, parallel to the axis through the center of mass, and separated by a perpendicular distance d from the axis through CM, the axis through the center of mass. Okay, so this is the moment of inertia about an axis that passes through the center of mass. And then if you want to find the moment of inertia about an axis that is parallel to this axis over here and separated by a perpendicular distance d, you can calculate the moment of inertia as the moment of inertia about this axis plus mass times d squared. Okay, all right, so that's what we call the parallel axis theorem. Now let's prove it. We're going to prove it for one-dimensional case. Okay, maybe let me go to the other side. Let's consider maybe a rod. Okay, so suppose we have this rod. Okay, let's say center of mass is uniform. All right, so we have this axis that passes through its center of mass. This is center of mass over here. Okay, so the moment of inertia through this axis is ICM. Okay, now we want to find the moment of inertia about another axis that's parallel to this one and that's separated by a distance d. Okay, so this moment of inertia is I. So our goal is to find the relationship between these two. All right, suppose this is our axis. Okay, so let's say this is a y-axis, let's say this is the x-axis. Okay, actually let me put the x-axis, the y-axis over here. Let me put it again. So let's see, we have this one over here. Okay, let's say it's the center of mass. So this is going to be our y-axis. Okay, our y-axis, and the moment of inertia about this axis is going to be ICM because it passes through the center of mass. This is the center of mass. Okay, now we want to find the moment of inertia about another axis over here. Okay, separated by a distance d over here. All right, now if you take a mass element over here, right, so this distance is x. So if you calculate the moment of inertia about this axis, this distance over here is d minus x. Okay, so this is my x-axis over here. From here is x. This is my r perpendicular. If I'm trying to calculate I over here, right? So I is the integral of, let's say you call this r perpendicular squared times dm. But r perpendicular, this distance over here is d minus x, right? D minus x. All right. So we can say that the moment of inertia about this axis over here is the integral of d minus x squared times dm. Okay. Now let's expand. This is the integral of d squared minus 2x d plus d squared dm. Okay, so we have the integral of d squared dm minus the integral of no, one of them is x. I'm going to put x over here. This is x over here. This is 2xd dm, and then you've got the integral of x squared dm. Okay, Now you see x is the perpendicular distance from this axis which passes through the center of mass. You see that's the perpendicular distance. So this represents the moment of inertia about the axis passing through the center of mass. Okay, so this is ICM. Okay, do you see that? This is our mass element. Its perpendicular distance from this axis x. Therefore, this integral represents the moment of inertia about the axis that passes through the center of mass. All right. Now, this d squared is a constant, so you can take it out. And the integral of dm is simply the total mass. So this one equals mass times distance squared. All right. Now, let's look at this one. D is a constant, and it is a constant, so you can take this is 2d, and then the integral of x dm. Okay. If you remember, this is a formula for center of mass. This is mass times the x-coordinate center of mass. But the center of mass for this rod is located at the origin, right? So xcm is 0. This is equal to 0 because the center of mass is at the origin. The center of mass is at the origin. Okay, the center of mass of this object is located at the origin, so this is 0. So we just have these two terms. Okay, so the main information about this axis, which is parallel to this one and separated by a perpendicular distance d, it follows is simply the sum of these two. Okay, so you've got I equals ICM plus m d squared. So prove it. Okay. Now let's look at some examples of using this formula. Okay. Now the moment of inertia about an axis passing through the center of mass of symmetric objects such as a sphere, a cylinder, a disk, and so on can be found in tables in textbooks. And then you can use this formula to find the moment of inertia about another axis that is parallel to the axis through the center of mass using this formula. Okay, so let's look at the following example. Okay. The moment of inertia, we have already obtained expression for this one in previous example, but let me write it. The moment of inertia of a rod, of a uniform rod of length L and mass m about an axis that passes through its center of mass, through its center of mass perpendicularly, is given by, we have already seen that, ICM equals ml squared over 12. The question is, give an expression for the moment of inertia about an axis, let's say, that passes through its right end, let's say its right end. So this is the problem. We have the rod. We know the main information about this axis, over here. is ICM equals m L squared over 2. Okay, we want to obtain the moment of inertia about this axis. Okay, that is parallel to this one. So that's our new moment of inertia. Now if the length of the rod is L, this is L over 2. Okay, so in this problem the perpendicular distance D between the two axes is L over 2. Okay, so we're going to use the parallel axis theorem, which is I equals ICM plus M D squared. Now LCM we're told is ML squared over 12, and D in this case is L over 2. Okay, so we have M L squared over 12 plus M L squared over 4. Okay, we take common 12, so that is ML squared plus 3 ML squared. We get the moment of inertia is ML squared divided by 3. So you see, we don't have to go through the integral to obtain the moment of inertia for this one. We can just use the parallel axis theorem to do it. Okay. Another example. Let's say we have a sphere of mass m and radius r. Okay, so we're talking about a uniform sphere of mass m and radius r. Okay, now you can find the moment of inertia about an axis that passes through its center of mass in tables in textbooks, and that is 2 over 5 mr squared. Okay, the question is to find the moment of inertia about this axis over here. Okay, so that is my I. That's what I want to find. Okay, so one condition satisfied, these two axes are parallel, and this distance over here is the radius, right? So d equals the radius in this case. All right, so the moment of inertia about this axis is ICM plus m d squared. As found from textbooks, ICM is 2 over 5 mr squared, and d is r. So that's it, we have simplified this. So this is, let's factor out mr squared. So that's 2 over 5 plus 1, or 5 over 5. So that is 7 over 5 mr squared. So this is the moment of inertia about this axis of rotation over here. Okay, so that is the parallel axis theorem. Now we're going to look at rolling kinetic energy. Rolling kinetic energy. Okay, now suppose we have this sphere that's rolling. So in this case, you see it's rolling, so we're going to have two kinds of kinetic energies. It has linear kinetic energy because it's moving linearly, but also it has rotational kinetic energy because it rotates as it's rolling. Okay, so let's use the following coordinate system. Okay, so let's our representative mass elements be over here. This is my dm, representative mass element. Okay, let its position vector be r, and then this is the center of mass. Okay, so this is the position vector of the center of mass, and let's say this is the position vector with respect to the center of mass. Okay, so this is a position vector of the center of mass with respect to our coordinate system over here, and this is the position vector of this mass element dm with respect to to the center of mass over here. This is center of mass. Okay, so we know that the kinetic energy of this object, let's say is dke, would be kinetic energy is half mv squared, right? So it'll be half, the mass is dm, and the velocity is the derivative of the position vector, right? So this is dr by dt squared. That's the kinetic energy of this particle. Okay, but this r over here is the sum of the rcm, the position vector of the center of mass, plus position vector with respect to the center of mass. Okay, so but this position vector over here equals rcm plus r prime. Okay, which implies that dr by dt is dr cm by dt plus dr prime by dt. Now you see this one over here is the velocity of the center of mass. Okay, this is the velocity of the center of mass. So this dr by dt over here is the velocity of the center of mass plus the velocity of dm with respect to the center of mass, which is dr prime by dt. Okay, now let's go back to this formula. So this dke, the kinetic energy of this small mass element over here, is half dm and then the square of this vcm plus dr prime by dt squared. Okay, and then of course we square this, we get half dm vcm squared, and then there's a cross term, half dm times 2 times vcm times dr prime by dt, and then third term, half dm dr prime by dt squared. Okay, so we have these three terms. So now let's integrate. So the kinetic energy, let me start from here maybe. The kinetic energy is the integral of, for the first term, which is, there's a factor over here, and then vcm squared dm. Okay, the second term, this one over here, the factor of 2 goes away, so you've got plus the integral of vcm, we have vcm times dr prime by dt dm, and the third term is the integral of half the integral of dr prime by dt squared times dm. Okay, now let's look at this three terms separately. This one over here, you see this expression over here does not depend on the center of mass. This velocity is shared by all the mass elements. All of them move with the same center of mass, so this can be taken out. So this equals half vcm squared times the integral of dm, but this one is the total mass. Okay, so this expression is simply half mass and vcm, that's the velocity of the center of mass, squared. How about this one? This is a constant, we can take it out, you see, because all the mass elements move with the same velocity at the center of mass. So if you take that out, you've got vcm dotted by dr prime by dt dm. Now you remember this formula? This formula is, this one over here is a formula for the velocity of the center of mass. This is 1, so it'll be total mass times VCM. But remember, this is the velocity of center of mass with respect to center of mass. This R prime is a position vector with respect to the center of mass. Therefore, this is the velocity of the center of mass with respect to center of mass. This equals 0 because VCM prime is velocity of center of mass with respect to the center of mass, with respect to the center of mass. Okay, so it's 0. So the center of mass is not moving with respect to itself. Okay, so this term is 0. This will go away. How about this one? So this will go away. So we just have these two terms left. How about this one? You see? This is the velocity of this particle with respect to the center of mass. Now, this is a solid object, so this distance is a constant, doesn't change. So the velocity of this mass element with respect to the center of mass can only be rotational motion. Okay? So this linear speed over here equals angular speed times the radius. Okay? So for this one, we have, this is the linear speed equals the angular speed times the radius. All right, so let's put them over here now. So this is half m VCM squared. This is 0, and this one is half the integral of omega r prime squared dm. Okay, the angular speed is a constant. All the particles are moving with the same angular speed, so you've got half omega squared, and this is the integral of r prime squared dm. Now you see this is the perpendicular distance between, you see the axis of rotation that goes this way and the mass. Okay, therefore this represents the moment of inertia about the center of mass. Okay, so this represents the moment of inertia about the center of mass. So this expression is half ICM omega squared. Okay, so the rolling kinetic energy, this implies the rolling kinetic energy. So the kinetic energy of a rolling object is half m, the velocity of the center of mass squared, plus half the moment of inertia about an axis that passes through the center of mass times the angular speed squared. Okay, so you see rolling kinetic energy has two terms. One term is linear kinetic energy, and second term is rotational kinetic energy. It has both kinds of energy. Now you see this, the angular speed and the linear speed VCM are related. Okay, look, if you take this point over here, it's moving with the same velocity as the center of mass. Okay, this point of contact over here, and its linear speed is angular speed times the radius. Okay, so we have, if the radius of the sphere is r, then you've got VCM equals r times omega, where r is the radius of the sphere, the radius of the rolling object. Okay, so that's how we calculate the moment of inertia object. Now let's look at an example. Calculate the kinetic energy let's say, of a sphere of radius, let's say 0.2 meters and mass 2 kilograms, that is rolling on horizontal surface, let's say with a speed of 10 meters per second. Okay, so here's the problem. We have the sphere over here. We're given the mass is 2 kilograms. The radius is 0.2 meters, and the speed is 10 meters per second. Okay, so it's moving this way, but remember, as it rolls, it's also rotating. All right, so that's how you calculate the kinetic energy. Ke rolling equals half m VCM squared plus half I CM omega squared. All right, now for a sphere, ICM equals 2 over 5m r squared. Okay, so let's simplify this. So the rolling kinetic energy is half m BCM squared plus half the moment of inertia 2 over 5m r squared. And remember, this v, this omega equals BCM divided by r. Okay, so let's put that in. This is VCM divided by r squared. Okay, let's simplify this. We get half m BCM squared. These two cancels out. Okay, so you've got 1 over 5. You see r squared cancel out. These two r squared cancel out, right? So you've got m BCM squared. Okay, and then we combine these two with a common factor of 10. So you got 5 plus 2m BCM squared. Okay, so that is 7 over 10 times mass times the speed squared. Okay, and that is 7 over 10. The mass is, I think, 2 kilograms, and the speed is 10. So that's going to be 140 joules. So the energy of this rolling object is 140 joules, which is the sum of its linear and rotational kinetic energy. Okay. Another example. Suppose we have this sphere rolling in this inclined plane. Okay, let's say this is 30 degrees. All right, and then we have this object rolling over here, starting from rest. Okay, the question is calculate its speed over here. Okay, the question is calculate its speed at the bottom. Let's say once again the mass is maybe 2 kilograms, the radius is maybe 0.2 meters, and so on. Okay, so the question is calculate its speed at the bottom. Now we're going to use principle of conservation of mechanical energy. You might say friction is not, what's rotating is friction, of course. Friction is conservative. But in this case, the effect of the friction is to produce rotational energy. So if you include the rotational energy, the energy is still conserved. So we're going to use the principle of conservation of mechanical energy to solve this problem. So we're going to say kinetic energy initial plus potential energy initial equals kinetic energy final plus potential energy final. Okay, now this is a rolling object, so the kinetic energy is half mass v squared plus the gravitational potential energy is mgyi. Oh no, I'm sorry, I have to include the rotational energy. So this is half mv squared, that is initial, and then half ICM omega initial squared plus the gravitational potential energy yi equals half m v final squared plus half ICM omega final squared plus mgyf. Okay, this is capital M. All right, now for my gravitational potential energy, I'm going to put my coordinate system over here, so which means according to coordinate system yf is 0, and this is y initial. Let's say this is 10 meters, so this is 10 sine 30, so yi is 10 the sine of 30 or 5. Okay, so yi is 5, yf is 0 according to this coordinate system. So this goes away because yf is 0, and this goes away, initial speed, because just rolling, initial speed is 0. Okay, so this is also speed divided by the radius, so this also goes to 0. Okay, if vi is 0, then the angular speed is also 0. So that's what I have right now. mgyi equals half m v final squared plus half ICM omega final squared. Now remember, omega final equals v final divided by the radius. Okay, all right, so we have the following: mgyi equals half m v final squared plus half, this is a sphere, so the moment finish as 2/5 mr squared, this one over here, and then this is vf over r squared. Okay, so let's simplify this. First of all, now you see the mass goes away. All right, so you've got gyi equals half v final squared, and then this 2 goes with this 2. Okay, this r squared goes with this r squared, so we get plus 1/5 vf squared. Okay, so we combine them together, 10. This is vf squared 5 plus 2, so you've got 7/10 vf squared equals this one, gyi. So vf equals square root of 10 times gravitational acceleration times yi divided by 7. Okay, and if you use gravity approximately 10, the square root of 100 times 5, yi is 5, 500/7. So the approximate is 490, that is approximately the square root of 70.